Okay, Organic Chemistry 1, let's start Chapter 5, which deals with Stereoisomerism. Big word, but we're going to cover what that means. So let's review what isomers are. It says isomers are compounds. They have the same formula, but there's two general types of isomers. The first one is constitutional isomers, and this is something that we've already looked at in the class. This is compounds that have the same molecular formula, but have a different constitution or a different connectivity of the atoms. The classic example that I always use for this is, let's say we had the formula C2H6O. Well, there's two different ways I could arrange those atoms. I could either make ethanol, which is CH3CH2. So let's do this. So this is CH3, CH2, OH, and this is ethanol, or I could arrange them in this way, where I have the oxygen between the two carbons, like so, and this is called dimethyl ether. So dimethyl ether, dimethyl ether. And you see that these two compounds have the same constitution. They're both made up of 2 carbons, 6 hydrogens, and 1 oxygen, but the way they're connected is completely different, and they have very different physical properties, different melting points, boiling points, densities, etc. But what we're going to focus on in this chapter will be the concept of stereoisomers. Now, stereoisomers are compounds that have the same molecular formula, but a different arrangement of atoms in space. So same molecular formula, but a different arrangement of atoms in space. And there are several examples that I could give you of this, but I'll just start with a simple one. Let's say you take a carbon atom and you attach it to 4 different things. So 4 different groups. Let's say we have 1, 2, 3, something in the back and something coming out here. Let's say on one position I have something green, over here I have something red, over here I have something blue, and here I have something yellow. So the carbon is attached to 4 unique groups. They don't have to be different atoms, just 4 unique groups. And I'll talk about that a little bit more. And if I draw the mirror image of that, so I'll need the right pen. If I try to draw the mirror image of that the best I can, Mr. Dion is no artiste, that's for sure. But if I try to draw a mirror image, it would look something like this, where I would have the red, and again, here's my mirror plane right here. Then I would have the yellow here, I would have the blue in the back like this, and I would have the green like this. So we have 2 mirror images of each other. Now these compounds are mirror images, but they are not the same compound. They're what we call stereoisomers, because they're both a carbon attached to a green, a red, a yellow, and a blue, but they are not the same, and I can prove it because they are not superimposable. If I take this molecule and I try to plop it on top of this one here, you see that the yellow, not really the way that I've written it here, yeah, but anyhow, the yellow and the green will overlap kind of, but you see that the blue and the red will not. And you might be saying, well, Mr. Dion, you just don't have them oriented in the correct way. But you could make models of these, and you would find that no matter what you try, you cannot overlap these 2 molecules. Let me prove it to you. If I switch over to my camera here, so like this, if I switch over to my camera, I've made a model of 2 compounds that exhibit stereoisomerism. So I have this molecule, it's a black sphere connected to 4 different groups. I've got a yellow, an orange, and the white, which is in my hand. I have its mirror image here, and it doesn't matter what I do, I cannot superimpose these on top of each other. I can get the blue and the yellow to overlap, but then you see that the orange and the white will not overlap. And it wouldn't matter how I rotated these molecules in space, they will not overlap. Much like my 2 human hands, they are mirror images of each other. However, they are non-superimposable. I cannot impose one on top of the other. And we're going to talk about that even more as we move along throughout this chapter. So, stereoisomers, compounds that have the same connectivity of the atoms but have a different arrangement in space. So the important word there, in my opinion, is the word spatial. They have a different spatial arrangement of atoms, and we're going to see several types of stereoisomers. Well, I can show you another type that we already looked at in this class. We talked about cis and trans isomers on a cyclohexane. So let's say you have this molecule, and here's the two-dimensional drawing. That wasn't very pretty, but if I do it like this, I have a methyl group going up and a methyl group going up. This is the Haworth projection. You can see the two methyl groups are on the same face of the ring, and so we call this cis 1,2-dimethyl cyclohexane. But if I have one of the methyl groups going up and the other one going down, and I draw its Haworth projection, I have trans 1,2-dimethyl cyclohexane. These compounds are stereoisomers of each other. It doesn't matter how I rotate them, even though they both have the same connectivity. If I take this compound and I try to overlap it on top of here, it does not overlap. The wedges overlap with one another, but the dash and the wedge will not. And it doesn't matter how I rotate this molecule, there is no way I can superimpose the two. Again, they both have the same connectivity, but the arrangement of the atoms in space is different. And so in order to give these compounds unique IUPAC names, we have to use the cis and trans prefixes to let the reader know that they are not identical. They have a different spatial arrangement of atoms. Well, there's another type of cis trans isomerism that we see, excuse me, in organic molecules, and that is when we have an alkene. Now, you must remember that when we have a pi bond and a carbon-carbon double bond, that we do not have free rotation around that bond. So if I just take this molecule that's shown here, cis-2-butene, I cannot rotate around this bond. And if you make any molecular model out of any cheap molecular model kit, you'll see that you cannot rotate that bond. So if I compare cis-2-butene, where the two methyl groups are on the same side of the double bond, and then trans-2-butene, where the two methyl groups are on opposite sides of the double bond, I see that these are also stereoisomers. Why are they stereoisomers? They both have the same connectivity. They are both a methyl group followed by a CH, a double bond, another CH, and another methyl group. However, their arrangement of the atoms in space differs from one another. Let's go back to the camera, and I'll show you a model of cis trans isomers. So I just happen to have some right here. This would be a trans isomer. You see that I put the two yellow groups on opposite sides of the double bond. And this would be a cis isomer. You see I put the two yellow groups on the same side of the double bond. Well, if you compare the two, they are not the same. They have a different arrangement of atoms in space. Now you might be saying, well, why can't you just rotate this? Well, you see that you have a double bond and you cannot rotate a double bond. There's free rotation around a single bond, but a double bond prevents rotation. And thus, this is another example of stereoisomerism. These two molecules are stereoisomers of each other. So stereoisomers, two molecules with the same connectivity. However, they have a different spatial arrangement of atoms, a different arrangement of the atoms in space. Give me a thumbs up if you follow me on that one. Are you with me on that concept? Good. Okay, well, let's try a practice problem. It just says identify the following pairs as either constitutional isomers, stereoisomers, or identical structures. Let's start with the top left-hand corner. If I take a look at these two compounds, would these be stereoisomers, constitutional isomers, or identical? Does anybody have an idea about this one? These two would be identical to one another. Exactly. Thanks, Tracy. These two are identical, aren't they? We'll just write here identical, because all that happened here was the ring flip, right? We just flipped the ring. Here we have up and axial. Here we have up and equatorial, right? If you were to draw the bond line structure of those, all you would draw would be this, you know, and you could even put that on a wedge for both of them. There's no difference between the two of them. They're both identical. What if we move on to the next one? So what about these ones here? On one of them, you see you have the two hydroxyls both pointing up. One is up an axial, one is up an equatorial. But on the next one, we have a hydroxyl going up an axial, and we have another one going down an axial. How would you describe these two? Right, they are constitutional isomers, but what's a better description? A more accurate description would be that they're stereoisomers, right? Because they have a different arrangement of the atoms in space. The first molecule, excuse me, this molecule is cis and this molecule is trans, and therefore these would be stereoisomers. So stereoisomers, a different arrangement of atoms in space. What about the next one? The next one, this one here, where I have a ring, I have this ether. This is called Tetrahydrofurion. This is called butanone. Anybody have an idea about this one? The one in the bottom left? Yeah, these are constitutional isomers, absolutely. So we'll just put here, both are C4H8O, and therefore these are constitutional isomers. All right, let's move to the top right. What about these two? These be stereoisomers, constitutional isomers, or identical? These two are identical, absolutely. Yeah, these two are definitely identical. If you were to take this molecule here, and if you were to rotate on this axis 180 degrees, you would end up with this. So these two are identical. Identical. There's no differentiation between those whatsoever. And the last one, you see that you have a double bond that is trans here, and then we have a double bond that is cis here. They have the same connectivity, but they have a different arrangement of the atoms in space, and so these two are stereoisomers of each other. Stereoisomers. All right. Well, there we go. That's a little bit of practice on stereoisomers and identical and constitutional isomers. Let's try another one. Let's just see if we can figure if something is cis, trans, or neither. So what about this one here? Would this be cis, trans, or neither? Yeah, this one is cis. Why is it cis? Because we have a hydrogen going up here and a hydrogen going up here. In order for something to be cis or trans, you've got to have two identical groups on the same side or the opposite side of a double bond. So this one would be cis. What about this one here? I think we already looked at this one. This one is cis because both of these groups are pointing up. This one is up. This one here is going to be trans because you have something that's up an axial. Then you have something that's down an axial. Let's see. This one, we already solved this one too, didn't we? This one here is trans. And my last question is this one. What about that? Would that be cis, trans, or neither? The one in the green circle. It's neither, isn't it, Zoe? Exactly. Yes, Kian. Yes, absolutely. So whenever you have two groups that are identical on the same carbon, it can't be cis or trans. It's impossible because this methyl group is trans to this one, but this methyl group is cis to this one. So there's no cis or trans, and therefore this is going to be neither cis nor trans. There we go, a little practice on that. Well, let's get back into this whole idea of stereoisomers and get into a little bit more detail. And you're going to see some concepts in here that I've already kind of let come out of my language a little bit, because cis trans isomerism is only one type of stereoisomerism. There are other important stereoisomeric relationships that we have to know as organic chemistry students. And in order to identify other types of stereoisomers, we have to be able to identify what are referred to as chiral molecules. And if you remember, I held up my hands and I said that they were non-superimposable mirror images. Well, that would mean that the human hand is chiral. Check it out. It says a chiral object, something that's chiral, is asymmetric. All asymmetric means is that it's not the same as its mirror image, or it's non-superimposable on its mirror image. Again, if you take a left hand, so if you take a left hand and then you take a right hand, right, they're mirror images, but you can't superimpose one on top of the other. And that was a demonstration I did a little while ago. And so again, you would say that a human hand is chiral. Let's take a look at another example. Let's say we have these kind of like John Lennon sunglasses here. If you have both of the lenses intact in the sunglasses, they are definitely superimposable upon each other, right? So you would say that this is not chiral. You would say these sunglasses are not chiral. However, if you were to remove one of the lenses from the sunglasses, so let's say one of the lenses fell out. Now, would this pair of sunglasses be superimposable upon this pair? No, it would not be. I'm going to draw these sunglasses in the red circle. I'm going to draw them above here. So let's see, you got one lens and you got the thing here. You got the next lens, you got this, and you've got this. So if I redraw what's in the red circle, I would have the shaded inside over here. Now, if I take that and I try to superimpose it on here, you see that they don't superimpose upon one another. Therefore, what I have in the red circle or in this red circle, those are non-superimposable mirror images to what's inside the mirror. Therefore, we say that the glasses with the lens poked out, we say that they are chiral. We say it's a chiral object. And so this pair of glasses we would say is achiral, and we would say that this pair of glasses is chiral. So now we've talked about human hands and we've talked about sunglasses. Well, you can imagine that's not going to be the focus of organic chemistry. It's not the study of Oakleys or anything like that. So let's move on, because chirality is important in what? It's going to be important in molecules. Let's just review a little bit here, or talk a little bit about why chirality is so dang important. It says that two chiral molecules are mirror images. They're going to have some properties that are identical. For example, if you run two chiral molecules that are mirror images and you check out both of their infrared spectra, or if you run a mass spectrum, you're going to get the same thing no matter what. However, this is where it comes in, just crazy, is that they have different pharmacology. Now that is of drastic consequence to human beings, isn't it? If you have two molecules that are chiral, they're mirror images, but they're non-superimposable. Well, there's many times where scientists have made one molecule that'll have some kind of desirable therapeutic effect, and then the mirror image will have some kind of horrible side effect. Okay, it could even cause death. And so we really need to know, when we're looking at an organic molecule that's chiral, we really need to know which mirror image are we looking at. So visualizing mirror images of molecules and manipulating them in three-dimensional space to see if they're superimposable is a skill, but it can be very challenging. And thus, if you're struggling with it at all, it is critical that you use handheld models. Now, these are the words of David Klein. Some students really find the molecular models super handy. Other people, not as much. That's a decision you need to make as a student. I don't force my students to buy a model kit. If you go into our syllabus, it says it's optional, but any inexpensive molecular model kit that you could buy would suffice in this class. And let's go back to this idea of chirality. Well, the reason I drew a model, or I made a model like this, and I drew a model like this a few minutes ago, is because chirality most often results when a carbon atom is bound to 4 unique groups of atoms. Notice it says 4 unique groups of atoms. It doesn't mean it has to be 4 different atoms. It could be 4 carbons, but they have to be on unique groups. Then we have what's called a chiral carbon. Sometimes we call it a chiral center. Sometimes we call it an asymmetric center or a stereogenic center. All of those are acceptable. You'll probably hear me use all of them. But again, if we take these 2 molecules here and we think about, okay, well, what if I had a hydroxyl? What if I had a hydrogen, an ethyl, and a methyl group? If you were to try to take this molecule and superimpose it upon this one here, what you would see is that the hydroxyl and the methyl are going to align, but you would end up with the hydrogen atom being over here, and those do not overlap. And therefore, these are mirror images. We can see the mirror plane, but they are not superimposable. Again, if you are unable to see this, it's helpful to make a handheld model and try to manipulate them and try to get them to superimpose. And what you will find is that they are never, ever going to overlap. So we say that they are chiral molecules. They would have different pharmacology, drastic consequences in the healthcare profession. When an atom like carbon forms a tetrahedral center with 4 different groups, it's called a chirality center. And again, sometimes I call that a stereogenic center. Sometimes I call it a chiral center. Sometimes I call it an asymmetric center. We have a whole bunch of different names. But let's take a look. It says, analyze the attachments for each chirality center. Let's look at this molecule here. We have a carbon highlighted in green. Why is that a chiral center? Because the carbon is attached to 4 groups. You've got the chlorine, you've got the hydrogen, which is going in back, you've got a methyl group over here, and then you have an ethyl group here. That counts as 4 different groups: a hydrogen, a chlorine, a methyl, and an ethyl. All 4 of those are different. Let's go to the next one. The next one, we have an alcohol. Well, on the carbon highlighted in green, I have the hydroxyl, I have a hydrogen, I have an ethyl group over here, and I have a propyl group over here. Ethyl is not the same as a propyl. These are 4 unique groups, and therefore the carbon highlighted in green is a stereocenter. If I go to this carbon here with the bromine attached to it, we have the bromine, we have a hydrogen in the back, we have this carbon here, which has 1 hydrogen attached to it, and then we have this carbon over here, which has 2 hydrogens attached to it. Those are 4 unique groups. Therefore, this is a chirality center or a chiral center. Like I told you, you could have 4 different carbon-based groups attached to your molecule. It would still be a chiral carbon. Let me give you an example. Let's say you had a carbon that has a methyl group attached to it, an ethyl group attached to it, an isopropyl group attached to it, and a propyl group. 1, 2, 3, like this. This carbon is a chiral center. It is attached to a methyl group, an ethyl group, an isopropyl group, and a propyl group. Those are 4 unique groups, and therefore that counts as a stereocenter, a chiral center, an asymmetric center. Give me a thumbs up if you follow me on the idea of stereocenters and identifying a stereocenter. Okay, let's try some practice, and let's see if we can find any chirality centers in these molecules. I'll tell you right now, some of these are more challenging than others, but let's start with the top left. If we start with the top left, so this guy here, are there any chiral centers in this molecule, yes or no? Would there be any chiral centers in here? Yeah, I'm with you, Tracy. I don't think there's any chiral centers in here because there is no carbon in here that's attached to 4 unique groups. Now, sometimes a student might think, well, what about this carbon? Isn't it attached to 4 unique groups? The answer is no. It's attached to a hydrogen. It's attached to a hydroxyl. And over here we have a CH2. Over here we have a CH2. So those 2 groups are identical, but let's look for a point of difference. Let's keep going. Next, we have another CH2 and another CH2, so we still haven't found a point of difference. And then they meet at the bottom here. So since there's no difference going this way or this way, there is no chiral center. No chiral center in this molecule. Zippo, zilch. Let's try this one here. Are there any chiral centers in this molecule? Any chiral centers in this one? What if I highlighted some of the carbons? What if I put this one in yellow, this one in green, and this one in red? Yeah, so Zoe, which ones do you think would be chiral centers? Or anybody? Absolutely, absolutely. The green and the red, they're both stereocenters, aren't they? Yes. Why is the yellow not a stereocenter? Because it's attached to two groups that are identical. This is a methyl group, and this is a methyl group. Therefore, this is not a chiral center. Could not be a chiral center. Impossible. So I'm going to erase some of this stuff here. This is not a chiral center, but what about the green? That's definitely a chiral center. Let's take a look at why. The carbon in green has a methyl group. It's also got a hydrogen. Then it has this isopropyl, and it has a sec-butyl. So the one in green is a chiral center. It is attached to 4 different groups. So let's put that in here. There we go. So let's just leave the hydrogen and we'll say chiral. That is a chiral center. And the one in green, we have a hydrogen going in the back. We have a methyl group over here. We have an ethyl group over here, and we have all this spinach over here. And so this is definitely a chiral center. There we go. So 2 chiral centers. Let's try another one. Maybe we'll just try one more, then we'll move on. What about this guy here? I'm going to help you with this one. Well, maybe I'll ask my students first. Let's say, I'll just ask you, in this molecule, are there any chiral centers? Yes or no? Yeah. All right. Somebody says, yes, there's 2 of them. I absolutely agree. There's a chiral center here, and there's another chiral center here. Both of those are chiral. If we just examine the one in red, you see that it's attached to a hydroxyl, a hydrogen, a methylene, a CH2, and then we also have this carbon over here, which is a carbon with a hydroxyl and a hydrogen attached to it. So we have 1, 2, 3, 4 unique groups. The same rationale applies to the carbon in blue. And so again, we have 2 chiral centers in this molecule. So right here, both are chiral. In the last one, we have 2 chiral centers. We have one here, and we have one here. I'll let you take a look at it yourself to see if you can figure out why both of these are considered chiral centers. Take a look at a molecule like vitamin D. It says identify and label all the chirality centers in vitamin D. There's a lot of chirality centers in here in this molecule. I'll just kind of help speed us along here a little bit, highlight some of these. We have one here, because keep in mind we have a hydrogen here, and this group on this side is different than this group down here, so that would be a chirality center. We also have a chirality center over here, and here, and here, and here. And those are all the chirality centers in this molecule. Every single one of those is a chirality center. So we have 5 chirality centers in vitamin D. 5 chiral centers in vitamin D3. Kind of cool. And you can review this on your own time to make sure that all of these are chirality centers. But something that you may have noticed already is whenever you have a CH3, whenever you have a methyl, or whenever you have a CH2, a CH3 or a CH2 can, excuse me, never be a chiral center, because the CH3 is attached to 3 hydrogens and the CH2 is attached to 2 of them. And so it's impossible for those to be chiral centers. Cannot happen. Not going to do it. Now, let's get back to this whole idea of non-superimposable mirror images. When we have stereoisomers that are mirror images that are not superimposable, like the human hands, the name that we use for those are enantiomers. So this is a word that's going to come up a lot now. I haven't used it until this slide, but enantiomers are non-superimposable mirror images. We'll put here like human hands. Human hands. They're mirror images, but you can't put them on top of each other. Now, only a chiral compound can have an enantiomer. If your compound isn't chiral, it's got no enantiomer. It doesn't exist. Now, how would you draw the enantiomer of this chiral compound? One way is to just draw the mirror image. So you literally try to reflect it over here, and Mr. Dion is not much of an artiste, but I draw the mirror image of it like this, like that, and there you go. So there's the mirror image, and therefore these two compounds are enantiomers of each other. But if you want a much faster way to draw an enantiomer, let me show you a much, much quicker and easier way. Here's the answer. Anything that's a wedge, you convert to a dash, and anything that's a dash, you flip to a wedge. And so you would redraw the molecule, same way, but here we have a wedge, and we just convert it into a dash, and done, just like that. So that means that these two are the same, okay? And these two, these are enantiomers. This is the same enantiomer drawn twice. So much faster to just flip a stereocenter. And that's what's being shown over here. So instead of trying to draw the mirror image, we just reverse the stereocenter. This compound here, this is amphetamine. So amphetamine. If you put a methyl group on here, then it becomes methamphetamine or crystal meth. Anyhow, that's neither here nor there. But you see that in amphetamine, we have one chiral center. If you want to draw the enantiomer of amphetamine, all you have to do is take the wedge and convert it into a dash. There you go, pairs of enantiomers. Now, this is not a chiral compound, and therefore, if you invert the wedge to a dash, it doesn't change diddly squat. These are both identical, and again, because these are not chiral compounds, this carbon is attached to two CH3s. So there's no chirality in there whatsoever. All right, that brings us to section 5.3, which is designating R versus S. And this is where I wanted to get with you today, or get to this point. And I want to cover this with you, namely what is called the Kohn-Ingold Prelog system. Kohn-Ingold Prelog, sometimes you'll see people refer to it as the CIP, Kohn-Ingold Prelog system. Because if we have two compounds that are enantiomers for each other, how would you differentiate between them with the name? How would you use nomenclature to relate a difference between these two? Well, both of these would be 2-chlorobutane, but they aren't identical, are they? Okay, and the way that we differentiate between them is that we use a prefix that is either R or S. And so if a compound is the R chirality center, then the enantiomer is going to have the S. Conversely, if a compound's chiral center is S, then its enantiomer will be R. So you're probably wondering, well, how do I know if a chiral center is called R or S? And these are very important rules that you're going to need for chapter 5, or quiz 5, and you'll need them for the entire rest of organic chemistry. But the good news is that they don't change. They're not going to change this year. If you decide to take Organic 2 a year from now, they're not going to change. The Kohn-Ingold Prelog rules are not going to change. So let's take a look. We use a stepwise procedure. Are you ready? Do a brief stretch, and let's cover the Kohn-Ingold Prelog rules. So Kohn-Ingold Prelog rules. Number 1. We use the atomic numbers to prioritize the 4 groups attached to the chirality center. So whatever atoms are attached to the chirality center, the higher the atomic number, the lower the number. So whatever's number 1 is going to have the highest atomic number, and then going down to 4, which would have the lowest atomic number. Then what you do is you arrange the molecule in space so that the lowest priority group faces away from you. If it's facing away from you, it's usually going to be on a dash. Now, this is a rule that I think there's a shortcut to this one, because oftentimes we'll have the lowest priority group facing towards us. So if it's facing towards you, then what you do is you reverse the stereochemical designation, and I'll show you some examples of that in a few seconds. So we'll put an asterisk by this one, and we're going to come back to this. Then you count the group priorities, 1, 2, and 3, around the stereo center, determining whether they go in a clockwise or counterclockwise fashion. If they go in a clockwise fashion, the stereochemistry is R. If they go in a counterclockwise direction, it's S. And this is another example where a handheld model can be super duper useful. Let's take a look at an example, because the example that I have in here is not the best example in the world. Let me give you a better example. Let's go back here and I'll draw something that I think is simple. So let's imagine let's go to a blank document. Make some space here. Some Taylor Swift blank space. So let's imagine we had a compound like this. Let's imagine you had chlorine up here. Let's imagine you have a hydroxyl over here. You've got your hydrogen in the back, and you've got a methyl group coming out in front. So CH3, like that. Okay, so what we're going to do is we're going to prioritize those atoms that are attached to the stereo center. This is our stereo center, and which one of these atoms has the highest atomic number? Well, it's chlorine. Chlorine has an atomic number of 17, and so it takes the highest priority. The second highest, we have oxygen, carbon, and hydrogen. Oxygen has an atomic number of 8, so it's going to be number 2, and then carbon has an atomic number of 6, and so it's going to be number 3. The hydrogen is already going in the back, and it is the lowest priority. Whenever you have a hydrogen, if it's going in the back, you're good to go. It's the lowest priority. So now we're going to count going around the stereo center, all around the stereo center, right? We're going to go around the stereo center, going from 1 to 2 to 3. So 1, 2, 3. Is my arrow going in a clockwise or a counterclockwise fashion? It's going in a clockwise fashion. Therefore, the stereo center is R. R, okay? We have an R stereo center, just like that. Now, remember I put that little asterisk next to rule number 2? The rule is this. If you have your lowest priority group facing towards you, so let me redraw this molecule like this. So let's say I had the lowest priority group coming towards me like this. Like let's say I have the hydrogen here, and then I have the methyl in the back, like this. If the lowest priority group is coming towards you, so the lowest priority group is coming in the front, then what you do is the same exercise, but after you've designated the stereochemistry, you reverse it. So if it's R, it becomes S. If it's S, it becomes R. So we do the same treatment. We have 1, 2, and 3. We follow the arrows, 1 to 2 to 3, and we're going clockwise, which would be R, but since the lowest priority group is coming out in front, we reverse it, and it becomes S. And so the stereo center here would be S. Give me a thumbs up if that makes some sense to you. Please tell me it makes some sense. Yeah? Okay, let's try another example. Let's go back to the old slides here. So let's try this rule, or this one here. The reason I don't like this as the first example is because why the hell do they give you one where the hydrogen's coming out in front? Couldn't they have made it a little bit easier? So look, could anybody tell me based off of the rules, would this stereo center, would it be R or S based off of what I just told you? Not a trick question. Mr. Dion hates trick questions. Thanks, Nicole. Absolutely. It would be S, wouldn't it? Right? Because since the hydrogen is coming out in front towards you, you follow the numbers going from 1 to 2 to 3. which is clockwise. Clockwise equals R, but since the hydrogen is coming out in front, you reverse it to S. And so this would be an S stereocenter, like that. Nothing more to it than that. Now, something that you can do is you can rotate the molecule to put the hydrogen in the back. I do not recommend doing this. Okay, and if you study organic chemistry with Dr. Anderson, who's the chair at the department at UCCS, I mean, he's got a lot more experience than I do teaching organic chemistry, and I think that he would give you the same advice. I would not try to rotate the molecule. I find it very difficult to do that. Students tend to make mistakes. And so what we like to do is just reverse the order the way that I showed you. It makes it much simpler. Here I have it written down. It says rotating the molecule leads to errors. I don't recommend it. Just change the viewing angle. And if you end up with R, you switch it to S. And if it's S, you switch it to R. And that's all you got to do. Now, what if you have groups attached to the chirality center that are similar? In that case, you look for a point of difference. You try to find some point of difference in order to prioritize them. Let's say we have a stereocenter like this one here. Obviously, the oxygen is number 1 and the hydrogen is number 4, or it's the lowest priority. But here you have a CH2, and then here you have a CH2. So which one is higher priority? What we do is we go away from the stereocenter and we look at what both of those carbons are attached to. So I'm going to erase that, and I'm going to erase this. What's this carbon attached to? This one is attached to a carbon, a hydrogen, and a hydrogen. So a carbon, a hydrogen, and a hydrogen. What's the other carbon, the one on the right? What is it attached to? It is attached to a carbon. It's attached to a hydrogen. So let me just try to be consistent here. So a hydrogen and a hydrogen. So I've got a hydrogen, and it's also attached to a hydrogen. There's no point of difference. All of these are tied. And so what do? We go to the next carbon, and we keep going until we find a point of difference. So now I'm going to investigate this carbon in yellow and this carbon in blue and see if I can find a point of difference. And that's shown over here. The carbon on the left, what's it attached to? It's attached to a carbon, a carbon. Remember, we're going away from the stereocenter, and it's attached to a hydrogen. What's the carbon on the right attached to? It's attached to a carbon, it's attached to a hydrogen, and it's attached to a hydrogen. So what I do is I list those atoms in the order of the highest atomic number to lowest, and we see that we have a tiebreaker here. Carbon has a higher priority than hydrogen because it has a higher atomic number, and therefore all of this has a higher priority than all of what's on the right-hand side. And so if we want to designate the stereochemistry, look, let's just erase all this. We end up with this. We have 1, 2, 3. So we go from 1 to 2 to 3, which would be S because we're going counterclockwise. But remember, the hydrogen's coming out in front, so we reverse it, and it becomes R, and there we go. We have an R stereocenter. It's one of those things that you really have to practice. But once you get the hang of it, students usually get very quick at designating stereochemistry. We analyze those atomic numbers going one layer of atoms at a time until we find a point of difference. It's got nothing to do with the sum of the atomic numbers or anything like that. We just go for the first point of difference, and that's it, my friend. That's it. That's all, as we say in French. All right. Now, if you have a double bond, it counts as 2 single bonds. So let's say, you were looking at this carbon. What's it attached to? It's like the first bond to oxygen counts as an oxygen. The second bond counts as another one. And then you've got the bond to hydrogen. So you would list them like that. And for rotating the molecule, there are some other tricks that you can use. If you swapped 2 groups on a chiral center, it reverses the stereochemistry from S to R or R to S. And another rule that always makes me chuckle is, and I don't think I have it here, if you switch two groups at this, or switch two groups simultaneously, you end up with the same molecule. So the summary of all the rules is shown here. You identify the 4 atoms directly attached to the chiral center. You put the lowest priority group in the back. You order the groups 1, 2, 3. If it's going clockwise, it's R. If it's going counterclockwise, it's S. If the lowest priority group is coming out towards you and you get R, you reverse it to S. If you get S, you reverse it to R. And that is the Kahn, Ingold, Prelog rules. This is the structure of L-Dopa. So if you've ever wondered about L-Dopa, here's its structure. There's one chiral center in the molecule. We have the hydrogen coming out towards us like this. I'm going to give you a second. Could anybody tell me if this chiral center is R or S? Anybody? I'll give you a second to try it. Would this one be R or S? Anybody have an idea? Cool, I get some answers. Okay, now I got a split. I got both answers. We'll take a look at it. Okay, well, let's see if we can order the groups. If I have the hydrogen, the nitrogen, I've got a carbon here, and I've got a carbon here. Out of all those atoms, you've got hydrogen, nitrogen, and carbon. Which one has the highest atomic number? Excuse me. What is the highest atomic number? All of these. Yeah, there's oxygen in the molecule, but that's not one of the atoms that's directly attached to the chiral center, right? You have to, here's the chiral center. Here we have a carbon. Here we have a carbon. Here we have a nitrogen and a hydrogen. We only look at the atoms that are directly attached to it. The nitrogen has the highest priority. So this is going to be number 1, and the hydrogen is going to be the lowest. So now we look at the 2 carbons. What's the carbon in red attached to? The carbon in red is attached to oxygen, oxygen, and oxygen. The carbon that's highlighted in green, what's it attached to? It's attached to a carbon. So we have a carbon, and then it's attached to a hydrogen, and then it's attached to another hydrogen. Again, we're going away from the stereocenter. So where's the tiebreaker? Oxygen has a higher atomic number than carbon. Therefore, this must be group number 2, and this would be group number 3. So now we follow the arrows, or follow the numbers. We go from 1 to 2 to 3, like that. That is going clockwise. Clockwise equals R. But since our hydrogen is coming out in front, we reverse the R to S, and therefore this is an S stereocenter. Just like that. Let's try one more. So let's go back to our blank document here, and let's see if we can solve another one. There we go. So what if I gave you something like this? So let's try this molecule, and then we'll try this molecule. So I want you to determine the stereochemistry here and here. Could anybody tell me what the one in yellow is? Would it be R or S? Talking about just the one in yellow. We'll start there. Okay, I got somebody with an answer. Let's take a look at it. Let's see here. Let's zoom in. We have a hydrogen going in the back. That's going to be our lowest priority group. We've got an oxygen coming out in front. That's going to be our highest priority. Then we have a carbon over here, and we have a carbon over here. What's the carbon in red attached to? It's attached to 1, 2, 3 hydrogens. Therefore, it's attached to HHH. But the carbon in blue is attached to this carbon and these two hydrogens. So it's attached to carbon, hydrogen, hydrogen. Here's my tiebreaker, the carbon. Therefore, this is going to be group number 2, and this would be group number 3. So I follow from 1 to 2 to 3, which is counterclockwise. My hydrogen is going in the back. Therefore, this is S. Great. Let's try one more, and then we'll call it a day. If we look at this stereocenter, bromine definitely has the highest atomic number. Then we have a hydrogen going in the back. It's got the lowest priority. Then we have a carbon here, and we have a carbon over here. What's the carbon in red attached to? It's attached to a carbon, it's attached to a carbon, and it's also attached to a hydrogen. Remember the double bond, each bond in the double bond counts as a single bond to that atom. Then if we go to the carbon in blue, it's attached to a carbon, it's attached to a hydrogen, and it's also attached to another hydrogen. Where's our tiebreaker? Our tiebreaker is right here. And so this would be our second highest priority group, and this would be third. So we go from 1 to 2 to 3, which is going clockwise. Our hydrogen is in the back, and therefore this stereocenter, since we're going clockwise, is R, and this is an R stereocenter. And just like that, we got it all done. We were able to identify a couple of stereocenters. So stereochemistry is something that definitely needs to be practiced, but there are lots of great practice problems in our textbook that go over all kinds of different problems, and you can practice just R and S and R and S until you master it. I'll be honest, it usually doesn't take students all that long before they feel pretty confident about their abilities to identify stereocenters as being R and S. Let's go back here, and if you go into chapter 5 in our textbook, we have covered today sections 5.1 to 5.3. On Thursday, we're going to cover 5.4, 5.5, 5.6, 5.7, 5.8 a little bit, 5.9, 5.10 we're going to skip. It says resolution of enantiomers. That is the only section we'll skip. Will be 5.10, and then we'll go into 5.11, which deals with E and Z. All right, and that'll cover all of chapter 5. So I'm going to stick around for a few minutes, but if you have any questions, I'll be here. And if not, that's all good. And don't hesitate to shoot me an email if you have any questions.